Welcome to 5.4. Today we're going to put the fundamental theorem to work by solving some area problems. So let's just review the fundamental theorem of calculus. Part 1 says the derivative of the integral from a to x of f of t dt is simply f of x. And Part 2, this is the workhorse, says the integral from a to b of little f dx is big F of x evaluated between a and b, so that straight bar notation means f of b minus f of a. And here, big F is an antiderivative for little f. So let's review part 2. Let's evaluate this integral here. First, we need an antiderivative. So this is equal to, not arrow, 1/4 sine of 4x by the Bible or either by logic, because the derivative of that function is cos 4x. And then here I put a negative pi over 12, and up here I put a pi over 8, and that's equal to, I'm going to factor out the 1/4, and I have sine 4 times pi over 8 is pi over 2. I'm simplifying here, and then minus sine of negative pi over 3. All right, and that's equal to 1/4. Sine of pi over 2 is 1, and sine of negative pi over 3, let's look at negative pi over 3 on a unit circle. It's down there. So sine of negative pi over 3 is negative root 3 over 2. So we could clean this up a little, 1/4, 1 plus root 3 over 2. And you could distribute the 1/4 or not, I don't think it matters. Okay, now let's do some area problems. Let's find the area of this region here. So the area is going to be equal to, by my formula at the top of the page, I want integral of top curve minus bottom curve. So the top curve is 4, and the bottom curve is secant squared x. That's a dx, and now I want to figure out my limits. I know my first limit's going to be 0 because my picture is only in quadrant 1, so this is a 0. And then I need to find this number here where these two curves meet. So what I'm going to do, we'll call that b, we'll set secant squared x equal to 4. Set the two curves equal to each other. Now secant is 1 over cosine. So if I flip both sides, I get cosine squared x is 1/4. I took the reciprocal of both sides of that equation, and that gives me cos x is plus or minus a half. Well, I'm in quadrant 1, and the first time that cosine x is equal to a half in quadrant 1 is when x is pi over 3. So that's my value of b, pi over 3, and that's my upper limit up here on the integral. Okay, so now let's integrate. Drop the integral sign. This is equal to 4x minus an antiderivative of secant squared x. Well, the derivative of tangent is secant squared. So tangent x, straight bar, 0, pi over 3. So this is equal to 4 pi over 3 minus tangent of pi over 3, all minus 0 minus tangent 0. Now, tangent of 0 is 0, so this whole expression in the parentheses is 0, and our final answer is 4 pi over 3 minus root 3. All right, let's do a couple more. In this problem, the picture's not given to us, so we need to figure it out. We want the area bound by the x-axis and sine x over the interval from negative pi to pi. Well, sine of negative pi is 0, sine of 0 is 0, and sine of pi is 0. And the curve looks like this. So I'll call this region A and this region B. We're going to do two setups, and we'll evaluate the second setup. So the first setup doesn't use symmetry. Area is equal to, now we're going to need two integrals because top curve and bottom curve change halfway through that interval. So the area of region A is the integral from negative pi to 0 of the top curve, which is 0. The x-axis is y equal 0. The bottom curve is sine x dx. You could, yes, just write that as negative sine x if you wanted to, but I just want to illustrate top minus bottom. And then we're going to add on the area of region B, which is the integral from 0 to pi, and now the top curve is sine x and the bottom curve is 0. And yes, you could leave off the 0. Okay, so that's one setup that would require doing two integrals. The other setup uses symmetry, and the area of both region A and B is equal to twice the area of region B. So we're just going to find the area of region B and multiply by 2. So this is 2 integral 0 to pi of sine x dx. I'm leaving off the minus 0. That's 2 times an antiderivative for sine x is negative cos x. So I'll put the minus in front of the 2, straight bar 0 pi. And that's negative 2. And then there's a lot of minus signs going on here. So I definitely want to factor that out. Cosine pi minus cosine of 0. That's negative 2. Cosine of pi is negative 1. And cosine of 0 is 1. So negative 2 times negative 2 is 4. Let's do one more. And this last one just asked us to set up an integral for the area of the region. Do not evaluate. It's really important that you know the difference between giving an integral as your answer, which is a setup, and evaluating. So for example, in the previous problem, if I had been asked just to set up an integral expression for the area of the region, there would be 2 correct answers. One would be integral from negative pi to 0 of negative sine x dx plus integral from 0 to pi of sine x dx. So that would be a correct answer. And so would this. This one uses symmetry. Typically, I wouldn't use symmetry unless I actually had to evaluate the integral. If I'm just doing a setup, I probably wouldn't use symmetry. And we only actually evaluate the integral, that would be this, and getting a number if we're asked to do that. So let's go down to this problem here. We've got 2 parabolas, y equals 5x squared and y equals x squared plus 16. We want to find an integral for the area of the region bound by those 2 parabolas. So let's see where those 2 parabolas meet. Let's set 5x squared equal to x squared plus 16. So that would be 4x squared equals 16. So x squared is 4. So x is plus or minus 2. So the curves meet here and they meet here. And to find the y value of where they meet, we could just set x equal to 2 or negative 2 into either formula because the y values will be equal there. And we do that and we get 20. So y equals 5x squared goes through the origin, looks something like this. And y equals x squared plus 16 crosses the y-axis there at 16, and it also goes through those 2 points. So we got a setup that looks something like that, and we want the area of this region here. So the area is equal to, we don't need 2 integrals because top curve and bottom curve never change over that interval. So integral from negative 2 to 2, the top curve is x squared plus 16, and the bottom curve is 5x squared, and a dx, and then we'll do a little bit of cleanup. This is equal to negative 2 to 2 of 16 minus 4x squared, dx. And there you have it. That's the setup. We would stop there. Evaluating the integral means going on and finding the actual area, and you can do that on your own if you want. I did it and I got 128/3. And just one last comment. If you actually did want to find the area of the integral and evaluate it, it would be better to use symmetry because we love 0 as a limit. It just makes things easy. And so this integral here that I have in the circle is equal to twice the integral from 0 to 2 of 16 minus 4x squared dx. And that would actually be easier to evaluate than the other integral that I have. Okay, and that's the end of this section.